We have one more order of business before we see how the singular value decomposition applies. And the key here is to see that SVD can be written as a vector equation. Now, this is very similar to the diagonalization decomposition theorem for square matrices. But since we're dealing with non-square matrices, where A is an m by n, the decomposition is going to be a little bit different written in vector form. So here I've just expanded out. We recall that A is equal to U times some matrix sigma times the V transpose matrix. And what I want to quickly point out as a reminder is that V contains as its rows, or V transpose has rows that are eigenvectors of A transpose A. And the key here is that they are the rows of V transpose. They're the columns of V, but we really don't do anything with the V matrix necessarily. Until we prove that the SVD works and why we're doing these weird esoteric things. So sigma, we recall that what that has is that's going to contain along its diagonal. So it's a diagonal matrix, meaning there's zeros everywhere off the diagonal. There's just the diagonal that contains the sigmas, and then there's zeros on both sides of that diagonal. And so the way we write that is the diagonals contain the sigmas, the sigma i's, sigma 1 all the way up to sigma n. And recall that that is the same thing as writing the square root of lambda 1 all the way up to the square root of lambda n. And the lambda i's, and I'm just referring to all the lambdas are of the A transpose A matrix. So everything comes back to this A transpose A matrix. And then U contains as its columns, it has columns that are functions of the eigenvectors of A transpose A. So it's going to be A times Vi over sigma I. And that's going to be for I runs from 1 to m. Okay, so let's write this expansion out in a little bit more of a product form. So here what we have to realize that this is U is an m by m matrix, sigma is an m by n matrix, and V transpose therefore is an n by n matrix, giving us an m by n product. Now let's go ahead and carry out the multiplication of this and see what we come up with. So in our product between U and sigma, which we'll carry that out first, and by the associative property, we can multiply any two matrices we want first, as long as we don't change their order. So if I multiply U and sigma, the thing that we should notice is that we're going to take each of the columns in the A matrix, in the U matrix, and multiply each of those columns by the corresponding scalars in the first column of the sigma matrix. So we're going to take sigma 1, we'll multiply P1, and then we'll have a bunch of zeros from there, multiplying P2 all the way up to Pm. Now we are going to have exactly m elements, m rows in the sigma matrix, because recall this is an m by n matrix. This is an m by m matrix. So the only non-zero vector that we'll get out of this product will be sigma 1, P1. So we'll form a new column, which will just be P1 scaled by sigma 1. And then when I repeat this for the second column, now I will have the only non-zero element will be in the second row, and that will therefore scale the only non-zero scalar corresponding to P2. So that will give me sigma 2 times P2. Now, if I carry this out repeatedly, eventually I'll get down to sigma m. Now, there are a couple of cases here, but we're not going to make a big deal out of this because depending on the size of A, if there's more rows than columns or more columns than rows, this could look slightly different. But here I'm kind of assuming that m is going to be smaller than n. Okay, so now eventually we'll get down to this column here, the mth column, and that will produce, and I'll just sort of write here, dot, dot, dot. Eventually we'll get to that nth column, and that will give me the only non-zero vector will be sigma m times pm. And then from there, I'm only going to have 0 columns all the way up to the nth column here. So basically I'll have a 0 column here, and I will have 0 columns only from there on out. Okay, so we can see that basically this product between u and sigma is going to contain as its columns the sigma times the corresponding p vector. And now what we want to carry out finally is the product between u sigma, which we now have, I'll just put that in parentheses, and the V transpose matrix. So this product will be sigma 1 P1, sigma 2 P2 is the second column, all the way up to sigma M PM, and then a bunch of 0 columns, all the way up to the nth column. Now, one way that I could think about this is in this special case right here, here are m columns. This is going to be m columns, but this goes all the way up to n. This goes all the way up to n. Therefore, I'm going to have n minus the m columns that I already have. That's how many more columns of zeros I'm going to have. I'm going to have n minus m 0 columns in this case. And now I'm going to multiply that by the V matrix, which contains as its rows the transposes of the eigenvectors, of the n eigenvectors, V1 transpose, it's going to be a row, all the way down to Vn transpose. So again, we're only going to have, in this case, I'm going to take this out real quick because we're going to have, we definitely have those m eigenvectors here, but then potentially we're going to have all the way down to Vn transpose. Okay, that's again, I'm assuming in this example that we have fewer rows than we do columns. So if I look at these products, this vector here will multiply this vector here, this vector here, and this vector here. And then the second column here will multiply the second eigenvector here, all the way down to the mth column with the mth eigenvector, and then a bunch of zeros after that. So if I expand this out, I'll have sigma 1 P1 times V1 transpose plus sigma 2 P2 times V2 transpose, all the way up to sigma M PM times VM transpose. Now the reason I'm not going to write out the remaining terms is because they're going to be multiplied with the 0 vectors, and those are going to yield 0 matrices. Wait a minute, matrices? What do you mean matrices? I thought these were vectors multiplied with vectors. Well, the key here is that each of these p vectors in the U matrix, they're going to contain, they are m by 1 big. So this is an m by 1 vector. But V1 transpose, since all of the eigenvectors are n by 1, this is a 1 by n row vector. So this will be 1 by n. And similarly for all of these are all the P's are m by 1s, all the VI transposes are 1 by n. And this is important here because what I'm trying to show is that this still produces the A matrix. This is the A matrix, and therefore this better equate to an m by n sum of terms. So all of these individual terms, this is a scalar, these are scalars for all of these guys. These are individual scalar. And when I combine these terms, this product right here is an m by 1 times a 1 by n. So this is going to yield, this individual term will yield an m by n matrix. And this is the outer product, the product between a column vector and a row vector. And same thing with this term, this will yield another m by n matrix all the way up to the mth m by n matrix. And when I add together m by n matrices, I get a m by n matrix. And so this is the full-on vector decomposition. Now these are still producing matrices, but I've written it as products of vectors. And so in general, what we've just established is that we will, in theory, have n of these, but some of them are going to potentially be zeros. So we're just generalizing this now to the case where n could be bigger or smaller than m. But the point is, all of these terms are going to form individual matrices. And since they each form individual matrices, there might be some power in thinking about, could I potentially omit some of those matrices? And this is what image compression is about. If we omit some of these matrices, we save data and we get a compressed image, which is going to have lower resolution, but which will require less data. Now we'll talk in the next video about why this is going to be significant in compressing images.